Welcome back. In the previous session we have seen a little bit introductory part of wave optics, and in this particular topic we'll be discussing about the main backbone of this particular chapter. To understand the concepts in this chapter, we should have the idea of this particular topic which we are going to discuss now, and that is nothing but Huygens principle. So let us recall once what we discussed in the previous session. We have discussed about what is wavefront, how many types of wavefronts are there. Basically speaking, we have wavefront is nothing but the shape of the wave. How does a wave travels, or how does the shape changes when a wave advances in forward direction depending upon the source. We have basically three types of wavefronts, that is spherical wavefronts, which are generated from a point source, and a cylindrical wavefront which is generated from an extended source like a tube light, and a plane wavefront. These plane wavefronts are generally considered when the source is very far, we can say simply infinite distance from us. And if you just come to the principle, Huygens principle, it clearly demonstrates how does a wave advances from one place to the other place. If you look into the definition clearly, here each point of the wavefront is the source of a secondary disturbance. Here consider the point O as a main source, a light or a illuminating body, or we can consider a sun as a main source. The point O is the main source, and each point on the wavefront is a source of secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. These wavelets are called secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at a time t seconds. Let me explain you clearly. Consider this as a point source, and from this point source we have a wavefront here. As it is a point source, we will be having this to be a spherical wavefront, and on this particular wavefront I have just kept some dots named as A, F1 and F2. According to this principle, these points behave like this source, but they are secondary. Here it is primary, and as it is emitting the wavefront, these also start emitting the wavefronts. So they are emitting the spherical wavefronts, and the line joining, which is called a common tangent, all those spheres, is the second position of your wavefront. So the wavefront F1, A, F2 has been advanced to G1, A1 and G2. How it travels? Suppose you know that a very basic formula, speed is equals to distance traveled by time taken. Consider the speed of wave to be v, and the distance traveled to be d, and the time taken be t. From here I will be taking d is equals to vt. That is, the distance traveled by a wave in a time t seconds is given by vt. Here I am demonstrating this vt. Here it is vt. So from this point the wave has traveled to a distance vt. From this point the wave has traveled to a distance vt. From this point the wave has traveled to a distance vt. Because it is a wave and the velocity is common and the time is also common, so we will be getting equal distance. So these spheres are nothing but of same radii, and the tangent drawn here will be the second position, or the position of your wavefront after a time t seconds. Again we can say, locate some points. They are the points. Again they behave like a secondary sources, and we will be getting the position of your wavefront after a certain time interval. So like this we can explain the advancement of wave using this principle. What is this principle? Huygens principle. What does Huygens principle say? Huygens principle demonstrates that each point on the wavefront is the source of a secondary disturbance, and the wavelets emanating from these particular points spread out in all directions with the speed of wave. These wavelets are called as secondary wavelets, and if we draw the common tangent to all these spheres, we obtain a new position of wavefront at a time t seconds. Now we may get a doubt. Here the wave is advanced in forward direction. Does the wave advance in backward direction also? According to this principle, it should advance in backward direction also. Here we will be getting a common tangent. So here we will be having the wavefront in backward direction also. But there is a rule called Kirchhoff rule. What does this Kirchhoff rule explain? The intensity of wave is directly proportional to cos square theta by 2. Based on this rule, we can explain the intensity in backward direction as well as intensity in forward direction. So here theta is the angle made by the wave along the direction of the light. So if you take in forward direction, the wave is advancing in forward direction and the light is also moving in forward direction. The theta is 0, we'll be getting I to be maximum as theta is 0. But if we come towards backward direction, the light is advanced in a forward direction and this is taken to be in opposite direction. This angle comes to be 180 degrees. So theta by 2 will become 90 degrees. So cos of 90 I will be 0.